When working with sensors or any external devices, oftentimes you'll need to receive numbers that are pretty large, into the thousands or even millions. If you're accessing this data through an I2C or serial interface, you can only receive 1 byte at a time, and the maximum value of a byte is 255. In this video, I'm going to show you how to combine or concatenate multiple bytes into one large value. I'm Lloyd, author of Practical Robotics in C++. Let's get right to it. If I had to summarize in one sentence, I would say that Practical Robotics in C++ is the book I wish I had years ago as a hobbyist, so I wouldn't have to spend as many years as I did to accumulate all this information. A byte is just a block of data that holds 8 bits of information. A byte is kind of the base unit of data that we either send or read from memory. As programmers, we don't usually concern ourselves too much with the details, and we just send one byte after another and let that be that. Under the hood, however, serial data transmissions can only happen 1 bit at a time. Each bit in a byte can hold either a 1 or a 0, and the bits are addressed from right to left starting at 0. The maximum value any byte can hold is 255. So how can we then send a large value like 65,535? If you're not familiar, let me introduce you to the ASCII table. Here you can see we can represent numbers as characters with ASCII code. So if you're typing with your friends on Facebook, through Facebook chat, and you send the number 5, the number 5 isn't actually going to be sent. The actual byte that is going to be sent is going to be a decimal 53. And if you were to look closer at the bit level, what you would see is 00110101. All the numbers, all the punctuation marks, special characters, and of course the alphabet are all encoded in the ASCII code. The alphabet starts at 65. I think the lowercase alphabet starts at 97. So one possible way to send a large number like 65,535 is to send one character at a time. So if we were to type that again over Facebook chat or something, the bytes we would actually be sending are 54, 53, 53, 51, and 53. But that's not really how we're going to do it when we're communicating with sensors. That's okay for chat features and things where we're sending strings of characters. But when we want an actual integer value, that's not what we're going to do. Instead of sending 5 bytes to represent 65,535, we could do that with just 2 bytes. If you're not familiar with how byte concatenation works, you may be wondering if a byte can only equal 255, and we add another byte to the end of that. Well, that still only gives us 255 plus 255, or 510, which isn't nearly big enough. But we don't merely add the bytes together when we concatenate bytes into larger units of data. If we wanted to represent a number bigger than what 1 byte could hold, we would concatenate the bytes or lay them end to end. So if you see the byte on the right, the values start at 1, then 2, then 4, and they keep doubling up to 128 is the largest single bit value in a single byte. Now when we concatenate the second byte, instead of starting over at 1, 2, 4, and 8, etc., we're going to start bit 0 of the second byte, which is now going to be called bit 8 at 256, which you'll notice is double the last bit in the first byte. And by doubling, as we increment over each bit, we end up with a final value for the last bit of 32,768. And if you add all those numbers up, you end up with 65,535 for the maximum value of a 2-byte bit of information. So here's the maximum values for 1 byte, 2 bytes, and 4-byte values. I threw on 4-byte because that's the maximum value for a 4-byte integer. An important thing to keep in mind going forward, when you have a value that you cast from one data type to another, the content of the memory address doesn't actually change. So let's say you declared a char, and we're going to name it val, and set it equal to z, the character z, because of the single quotes. Well, what you're going to end up with is this single byte somewhere in memory with these values here, 011111010. If you then try to display val in its native form as a character, it's going to output, of course, the letter Z. That's because if you add up the values for each bit that has a 1 instead of a 0, you end up with a sum of 122. If you look back at our table, 122 is the code for the character Z. And you'll notice the binary is in both of these little charts. If we then tell our computer, hey, I now need this value, val, to be interpreted as an integer, the output is going to be the number 122. And the binary value stored in memory will not have changed. The same is also true if you were to cast it into an unsigned integer. The first thing you need to know when you are interpreting data received serially or just reading out of memory from a sensor is you need to know what type of data you should be expecting, because when you receive that data, there's nothing in the bytes itself that says whether you should be interpreting the data as a character or an integer. So you're going to have to get that information from the data sheet or your friend Google, perhaps. The second thing you need to know is how many bytes that data will come in, because that information is also not encoded in the data you're receiving. So let's take a look at this status register for a sensor. There is 1 byte of data in every register, and this 27H is one way that they represent that we're looking at one register. So we know this is 1 byte of information for this register called status reg A. 27H, the H means it's a hexadecimal number. So you'll also see that represented 0x27 and 0x. That's how you tell your program it's a hexadecimal number and not a decimal number, because 27 hex is very different from 27 decimal that you're used to using. Now at the output register below it, you'll see in line 7.1.9, these are output registers, and there are 2 memory addresses. So I would query the device for 0x28 and 0x29, and I need to combine those bytes to get one value. Combining 2 bytes into a 16-bit value is as easy as shifting 1 byte over 8 places with the bitwise left shift operator and merging them with the bitwise OR operator. But which byte do we shift? The next thing we need to know when we are combining bytes from a sensor or serial data is something called MDM Ness. That is just whether the high byte comes first or the low byte comes first, also known as the most significant or least significant byte. So there's a couple acronyms to know. The first, if we just look at this single byte, the least significant bit is the one with the least value, and the most significant bit is all the way on the left, and it has the most significant value. It's worth 128. Notice that when we're talking about the bits, the abbreviation is lowercase. If we concatenate 2 bytes end to end, our least significant bit is still 0 all the way in the end. Our most significant bit is now the furthest on the left, which is now 32,768. When we have 2 bytes together, we not only have a most significant bit and least significant bit, we also have a most significant byte and a least significant byte. And now we capitalized MSB and LSB. The MSB is also known as the high byte, and the LSB is also known as the low byte. If we look back at line 7.1.9 from that data sheet, you'll notice that there is a clue for which is the high byte and the low byte, because there is an L right in the register name. So in this case, at memory register 0x28, that is going to be our low byte, and 0x29 is our high byte. Now that term that I brought up to begin with, MDM Ness. MDM Ness is how they describe whether something is big endian or little endian. Big endian means that the most significant byte, or the high byte, is at the lower memory address, or it comes first in a serial data stream. Little endian means the least significant byte is at the lower memory address, or comes first in a serial data stream. So look at this slide and tell me, looking at these 2 out registers, whether this value comes big endian or little endian. Look where our low byte is, and look at our 2 memory addresses. So this is going to be a case of little endian because our low byte is at our lower address. Another thing to keep in mind is that you're going to have to know how many bits are actually part of the value that you want to read. There are plenty of occasions where data will come in 16 bits or 2 bytes that you have to read to get the data, but not all of the bytes are actually in use. Look at this temperature register for whatever sensor I took this data sheet from, and notice that 4 of the bytes are simply not used. This is called 12-bit resolution, but it comes in 16-bit data blocks. A problem you need to be aware of when you're not using all 16 bits of data is you need to figure out how it's lined up. In the case of this temperature register, when we concatenate 2 bytes, we end up with a left justified 12-bit value. If it were the other way around and 4 bits of the high byte were unused, we would have right justified data. If our value is left justified, the bytes on the end are going to be filled with zeros, and we'll have a huge error when we tell our program to read the value. Sometimes when the resolution is less than 16 bits and we have to drop some unused bits, they make it pretty obvious like they did here. And other times it's not as obvious in the data sheet, as these are also all 12-bit values, and I had to find that out by printing to screen a whole lot of values and noticing that 4 bits were never changing. With a little Googling to support my theory, it was determined that these are just 12-bit values. The next thing you need to know is if you're reading signed or unsigned data. And that matters because remember when I said earlier that a byte can hold a maximum value of 255? That's assuming that this is an unsigned byte, and we can use all 8 bits to add up a value. When we're looking at a signed bit of data, the highest bit is used to denote whether the value is positive or negative, which only leaves us 7 bits for data. So the maximum positive value is 127 for a signed byte of data. The total range of a signed 8-bit integer is -128 to 127, which still gives us 256 values. Just half of them are negative. Finally, you need to know if there's a multiplier to apply to your information. I cover this a little more in detail in my last video on sensor data sheets. But usually when we interpret a bit of information, we get a raw value that is not the final value. Somewhere in the data sheet will be a scale that we need to multiply or divide that raw value by to end up with whatever unit we need from that device. Okay, finally, let's get to the nuts and bolts of merging bytes, which we also call concatenation. The first tool we're going to use is the bitwise OR operator. Hopefully you're familiar with your AND OR truth tables. But take a look. Let's say we received a least significant byte, and let's say we have a 16-bit variable named result, and we have initialized that to 0. In C++, we could say result equals result or LSB, and what that's going to do is, starting at bit 0, it's going to compare every bit, and if either LSB or the result bit is a 1, it's going to plant 1 into the output, which in this case we just assigned it right back to result. I need to stress that if you did not initialize your variable result, it could be junk data in there depending on the language you're programming in, or if you've used that variable before. So now what happens if we have 2 bytes that we need to concatenate and add to the variable result? First thing we're going to do is apply the bitwise left shift operator to the most significant byte. And that operation just looks like this: MSB, arrow, arrow, 8 bits. You can use a different number of bits than 8, depending on what you need to do. But in this case, we're using all 16 bits of data, so we will shift over the MSB 8 spaces. Now if we apply the OR operator to the most significant byte, we can populate the upper bits of the result. Of course, in this case, we neglected the least significant byte, and those are all zeros. We can simply add an OR operation, and finally our bit of code could read result equals result, or most significant byte shifted 8, or the least significant byte. And that is going to give us a final result that you see on the bottom. So that's easy enough if you have 16 bits of data that you're working with, and you're going to use all 16 bits. But if you only have 12-bit resolution, let's look back at our temperature register. How are we going to handle that? Well, you can see we need to ignore 4 bits on the least significant byte. So if we use that same bit of code where we shift the most significant byte over 8 and then just use an OR with the least significant byte as well, we get our desired 12-bit value. But if we try to interpret it now, it's going to be wildly wrong because all 16 bits will be included when the program tries to read the value. So now we need to use the bitwise right shift operator. If we look at this bit of code, this statement here I have circled in red is the equivalent of the entire 16-bit result. We can put parentheses around that part of the statement, shift the whole thing over 4. This is what our final line of code would look like. And as a result, our 12 bits are moved where they need to be. And if we ignore 4 zeros up at the top of the result, we get the perfect output when our program tries to interpret the data. This is exactly how I do it in this example program for an LSM303 accelerometer. First, I shift the most significant byte over 8 places, and then I conduct an OR operation with the LSB and the MSB. Once I have that 16 bits, I shift the whole 16 bits over 4 spaces, and I tell the program that I need it to be a 16-bit value. Then I take that whole thing, then I tell my program that I need it to be a floating point value as well. Finally, I apply the multiplier that I need to convert the raw value to Tesla. Finally, I assign the entire thing to this X value that we need for a robot operating system. So here's a look at some bitwise operators. I use C++, but I am pretty sure, I hesitate to use the word universal, but I'm pretty sure that these are all the same for Python, Java, Kotlin even. I think that pretty much wraps up this video. I know a lot of the times we can just download a driver program and not have to worry about these details, but I promise you, if you do electronics long enough, you're going to run into cases where the example programs aren't adequate for your needs or simply don't exist. You're going to have to write your own, and having just these few tricks up your sleeves takes the restrictions off you so you can do whatever is necessary with any sensor at all. Make sure you check out my last video on making sense of sensor datasheets for more information on decoding the sometimes daunting datasheets. There's a lot of information in there, and they're hard to read until you get used to. Also check out Practical Robotics in C++. I'll make sure there's a link in the video. As soon as it's in print, it's off at the publisher right now being formatted. And there's an entire chapter in there where we cover I2C and serial communications. I'm Lloyd, author of Practical Robotics in C++. I'll see you next time.